And now since this is the temperature, now let's say I want to analyze the voltage as well, maybe electric potential, right? So for that we need extra global variables, and we were the yeah here. Nope, nope, sorry, probes. Yeah, these are global variable probes, and yeah, it's actually luckily it's already selected E cell. That's the potential, right? So just write this maybe as potential. Uh, yeah, potential and battery one, right? And again another table, another probe. Make sure to do that so that you for temperature you have one table, and for potential you have like the another second table. And duplicate this one, name it as 2, and here put 2 again, duplicate, that would be 3, and that would be 3 here. So these will give you the different potential values and temperature values in each of the batteries. Now after that there are like three more things. That is the coordinate system. Now right now it is XYZ, right? But you know better than me, of course, probably, because when you deal with cylindrical elements, it's better to deal in the cylindrical coordinate instead of this global coordinate, right? So that now I will also specify how that like that differs, like how cylindrical coordinate and this one too differs, and how does that affect the result. Maybe at the end of the whole simulation I will explain that as well. But for the timing, let's just go with the coordinate system, extra coordinate system, that would be cylindrical systems. So this one I want this SYS2 to represent this one battery, right? So how you do that? In this you don't need to change anything. You do, in fact all you do is specify the origin actually. So so this 00, since this battery is actually on this 00 region, so we don't need to change that. So duplicate this one, that would be your system 3, but this needs to represent the second battery, right? For that we need to change this origin. Now notice this is in the X direction, and that's like the diameter of the battery, right? The rest of it like 00. That would be that. And create another one for the third one. Simply this time it's like probably 2 times the, yeah. So that's your like the coordinate system for the third battery. So the first, second, and third. This is very useful, like essential in fact. Otherwise you won't get the proper results. And where do you implement these? When you created this heat transfer in fluid, now select this solid one, right? So here the coordinate system is like it's global, right? Now here you see you have these options that you just added there. So select this one for the first battery, and for the second one select this third one, and for the third one select this fourth. Yeah, so that's really useful. I'll make sure to tell you the difference of how that differs, but at the end. And as for the materials, we need to add that definitely. And for that, open the like add material from library, because let's use some standard materials, maybe material library. Not really a good thing. Maybe built in, yeah, that's should do, because we need the air, right? Double click this one, and that gets added here. But you have to specify which domains you want the like to be treated as air. So for that, instead of all domain, you want to select the air domain, because that's the only air domain we have. And additionally, let's choose all these connectors and terminals to be made of aluminium, maybe something like this, and make sure to select only the connectors here. Now for the active material of the battery, for that we don't really have anything here, so we will be creating a blank material, and let's name it as battery active material, right? And select the 3 batteries, and instead of 1 2 3 just select these batteries set, right? Because that's what refers to all 3 of them combined. So the question is, what exactly do we need here? Now in the battery parameters, notice that we have row battery and specific heat, right? So you can simply just copy this one uh, into here. So we have like row C1, and for this one is like probably CP, capital or small, capital. So that's right. Now this thermal conductivity sorry about that. uh, you notice we have like two different variables, so we can't really put that there, right? So the best way to do that is actually say what you have to do is, this is where that thermal conductivity needs to go, right? So you can choose user defined, and instead of isotropic, I will like, it would be preferred if you use diagonal. That way you will have options to use. Now here you need to put these values. This will be like battery, and the second was, let's copy this one here, and diagonal, angular, and let's put this as R. Now this is actually a second order tensor, so you can study about that, why I'm putting this. It's like in the art direction, this is how I want the thermal conductivity value to be, and these are like other two playing other two directions, since I'm dealing with coordinate cylindrical coordinates, right? So that's why we have R and then these two. And the same thing needs to be done with here. So we have material user defined. Maybe you could have done this for like solid one at the start, and when you duplicate this solid one, like I did just before when creating this, that could have like saved you some time, but now I have to do it manually. So let's just get over with it. It's R again, user define, diagonal with that, and we need this to be R. Yeah, so that's our other than that, when you come here as fluid, make sure to select like this fluid to be gas or liquid, since this is liquid, right? That's actually better. Nothing to be here, since the air is still, is kind of natural convection to be precise. And other than that, we need the convection heat transfer, right? That's important. So we can add few stuff like heat flux and which boundary. Remember that when we built the geometry thing, we had this extra selection created specifically for this purpose, convection heat flux boundary. And then we want the convective heat flux, and we have this HT, heat transfer coefficient, defined, and for example this one HT, and then we have T initial. We can simply copy this one from there to there. Yep. Now once we are done with this, now we need to like set up the formulas and expressions in here. So the first thing is lumped battery here. So how much current we are applying, right? That's one thing. So let's see how much current we are applying. We have actually this I, so that's our current applied because it's in amperes, and then C rating will be multiplied with this, since that's how fast we want the charging to occur. So we copy that value here and multiply this with C rate. Yeah, so that will be our applied current. As for this is coulomb, remember we have this variable, so that is specifically to ensure like what is the maximum capacity of the battery. So that would be here. As for this like SOC, let's see, this is like the initial state, right? So let's say I wanted to start from the like one means like fully charged battery, right? So it will go from there to onward wherever it goes. Okay. Or maybe you can change that, but it's up to you. You can adjust those values like right now it's positive, so probably it will go like charging, or maybe you want it to discharge or something like that. You can go wherever you want. Like it depends on how you want to deal with it. Cell equilibrium. Now this is locatable, right? But we don't, let's say we don't want the locatable. We want it to like based on definition. So why based on definition? Because we already have these values defined, right? Remember, we have this ECO defined in the variable section, like these two. So that's so this is where these two comes in. Well, this one, and here we will select this voltage change with respect to time. Reference temperature, let's keep it to T initial, probably T. Yeah, so that's our initial temperature. And for voltage losses, this is where, now this is where the things that we define in here, analytic, this expression will be used at this point. Now I remember we have three terms here: activation energy, this E ETA levels like eta corresponding to 1C rating, and eta corresponding to J naught, eta corresponding to sorry, EA corresponding to tau, right? So these three things deal with three different phenomena that will be considered in here voltage as voltage losses. The first one is overpotential, and for that we have like these values like predefined here. So you can just simply like copy this one, maybe this one, simply copy that one and put it here. Voltage loss, that would be something like this, multiply by Arrhenius expression. This is like how you refer to the function, this one, analytic ARRH. And then in here you need to define which variable we are going like which is going to be used in here. Now let me check. Actually, I forgot which variable was that. It was a EA, that's for sure. But there are actually, I have quite a few variables in my mind. Yeah, it's the same variable, but it's a little bit different. I see, sorry about that. We can actually just copy this one here, just for the sake of convenience. Yeah. So yeah, so this E is basically the reference value that we have. You can check that. And this is like the extra reference value, and LB, this is the how the temperature of the whole battery varies, right? So just like this one here, we will have like expressions just like this one for the other two phenomenons. So let me just grab those real quick. Copy this one, and then you can just get these values. Now as for what these values are, now ohmic overpotential, you should understand like just by the word ohmic means this is basically the voltage loss because of the fact that there are so many different sorts of resistances in there in when you deal with the cell, right? The resistances that happens because of thermal, maybe thermal contact resistance, or maybe opposite every elements have its own resistance to current flow. That will also, so all of these kind of adds up to this one factor here, and Arrhenius expression is how you deal with them. Activation or potential is like normally when you are dealing with batteries, you have reactions, a lot of them, right? And every single reaction needs a certain amount of activation energy, but theoretical value of that activation energy is different from how when you actually do the like actual reaction, right? In or actual reaction you need a little bit more energy than the theoretical value. So this terms actually deals with that reaction, like more potential, more energy that you need for each reaction that occurs. So this deals with that extra energy that you have to supply during, in order to make sure that your reactions in the battery go smoothly, right? So this is like the extra energy that you provide to your cell to make sure like the flow is smooth. And this is for the reaction part. And this third one, this is referred here as concentration over potential. And what it is, it's basically you have this path, the path, like the path that you go from like point 1A, maybe A to B in a straight line, and the path that from between those two exact points, but in a porous media, because that would be different and more twisted, right? So this value is for that kind of thing. You can actually study that in online, maybe that would be really helpful for you, but at the present that's like how I can explain. And simply just copy this one. For battery 2, actually we need to set up these values. Just simply copy this one from here like this, and where is, yeah, this one, Q cell, and here this will be 1 2 for consistency. For electric potential, select the, from definitions we already have this whole thing set up, so it's just a matter of putting the values. And then voltage losses for this one as well, again, sorry, here. So you can just copy these one, and all you have to do is like change one parameter, like this LB2, because that's for battery 2 now. And for the other one you can copy this one, it's like here, this LB2 voltage losses, copy this sorry, this one,